Welcome to lecture 17 of MCS 471, numerical analysis. So today we close off our chapter on interpolation and take a much more geometric view on the problem of approximating functions and data. The main idea is that instead of considering one high degree polynomial over an entire interval, we will work with cubic polynomials of degree 3, but many cubic polynomials. So we will divide our interval in several pieces, and we will approximate every piece by a degree 3 polynomial. So that's the idea behind splines. Then very much related to splines are curves. So you can see a spline as an approximation of a function. A Bézier curve is where you have two functions. That one function is for the x-coordinate and the other function is for the y-coordinate. So Bézier curves are used in computer-aided design and manufacturing. So we will end with a Julia function, and there is a plot that is made with a Jupyter notebook posted at the course website. So let's dive in. So what's the problem? So we want to do a piecewise approximation with cubic polynomials. So the input data is very similar to the interpolation, except that now we actually impose an order on the points. One can consider now these points as the endpoints of the interval. We actually talk about nodes. We require that these cubic polynomials are interpolating. But a cubic polynomial has 4 coefficients, so the interpolating condition would only settle 2 of the coefficients. We will require, in addition, so to fix the cubic polynomials, that they have the same slope. So what that means is that the slope of one cube at the left interval is the same slope at the right interval. So in particular, how should you see this? Well, let's focus on this x3, f3 here. So let's pretend that this is the I equals 3. So we have one spline, which is S3. So S3 here has the same value as the S2. So the S3 at the point, so the previous spline takes the same value as the next spline. Okay. So I was saying that the I equals 3, but now I managed to confuse myself a little bit. So the S2 at the xi should actually take the same value, the same function value. So we have the same slope. So I think the bug here is with the I minus 1, so I will fix that. So we have at the same point that 2 adjacent splines actually take the same value, the same slope, and also the same second derivative. So we have the same concavity. So these are the conditions. Then we have an interpolating spline. So the cubic splines are actually written, so every spline starts from one data point. And you can see that the form of the cubic spline is such that the condition is actually automatically satisfied. So the condition that it interpolates, if you plug in x equals xi, then you see that all these terms here, they vanish. So this condition is automatically satisfied. So we see that. Then actually you can see that we have the additional conditions. These are the slope conditions, and now you see that here it is correct on the slide. So we have the slope conditions and the concavity conditions. So we have now three conditions. So actually we had four coefficients for our cubic spline. Now, one of the coefficients is by the form immediately satisfied. So in some sense, if you have given data, the f are often known with limited accuracy, you actually do not want to compute with them. So that's also the beauty a little bit from this interpolation condition. So it's automatically satisfied. We don't really have to do anything. And what I should have emphasized here too, the ith spline is living on the interval xi to xi plus 1. So we have the condition at the left, and then we have the extra condition that is imposed actually by looking. So there is one extra interpolation condition, and we have then the concavity and slope conditions. If you add up all these conditions, so we get to, this is 2 times n minus 2. We add n to this, so we have 3n minus 2 conditions. We have 3n coefficients, and we have 2 extra degrees of freedom. We say that the spline is a natural spline if the concavity at the endpoints is 0. All right, so let's now compute these coefficients. We will derive the conditions, so computing the derivatives of any general cubic spline and imposing the conditions. It turns out that actually looking at the concavity is actually easiest because you see when you plug in xi, you actually do have the value for the ci coefficient, which is kind of nice. I mean, the ci coefficient actually comes from the second derivative. The bi coefficient comes from the slopes, as we will see. So in a way, we encounter again the shape of the Taylor expansion. All right, so we have the ci condition, and then we have also a condition that is imposed by the next point. And will give us the condition on the di's. So in this slide here, we fix two coefficients. So we have the coefficient ei, that is defined by the concavity here, and then we have an expression for the di's. Now note that these are expressions, and what do they really mean? Well, actually, we don't really know what the SI is in full. So, in instance, we're not yet there. We will end up with a linear system in these SI, in these second derivatives of the SIs. So what this means, though, however, is that we can eliminate the ci and the di from our expression. We actually already know what they are, and now we're going to focus on the first derivative. So what are the conditions on the first derivative? So here, summarizing, what do we know about our cubic spline? We have expressions for the ci coefficient and for the di coefficient. So now what does bi needs to be? Well, let's compute some. So we have that condition that at the right of the interval, so the spline lives on the interval xi plus 1. Now at the right of this, we have that the function value must interpolate, and that will give us a condition on the BI. And you recognize the divided differences coming in as well. So what is here at the left is what we call the divided difference, the first divided difference that we computed in Newton interpolation. All right, so we have now also a condition that involves the BI, and we eliminate the CI and the DI from this. All right, so this gives us this relationship between the divided difference at the left, and then an equation that actually only involves the BIs. All right, let's continue rewriting this. So we rewrite the previous expression at the bottom of the previous slide. And we can see that we can simplify things a little bit. So we can try to get the divided difference back in there. So we simplify this by rearranging the terms. So the terms in the unknown as i's, so the second derivative, the concavity terms. So this gives us an expression. So the result here is this expression. So we have the BIs that are expressed in these divided differences. Now we have a spacing. Every length of the interval is hi. So we are introducing now notation to simplify this equation. So we have the BIs expression for BIs, CIs, and DIs, all in terms of this unknown TIs now. Fine. We are not there yet, so we have not used all our conditions yet. So the condition is that we have the slope conditions. So the slope conditions say that here we have that the spline at the node, at the xi node, the slope at the left of the left cubic spline should equal the slope of the right cubic spline. So in a way, all these slides are very algebraic now, but I hope that one should now have the picture from the beginning back in mind. So the fact that all these pieces look so smooth is because we have imposed these slope conditions. So the tangents actually agree. Or in another way saying that at point xi there is no discontinuity. The limit at the left is the limit at the right. That's also one way of saying this. Okay, we impose the slope conditions. By taking the previous, this cubic spline at the left, so we actually rearrange the indices. We have that the Si minus 1 at xi should actually equal what this expression is here. So this expression is this one here. All right. So we work this out and we simplify, getting now an expression in the TIs. So let's look what this means now in, so we have all the i's. Let's look at one example now. For n equals 4, what that gives us, or I'm sorry, let's continue with this. So we're going to see a numerical example in a minute. So we have our conditions on the slope, and that actually gives us equations in the TIs. So the purpose of this slide is to show that the slope conditions define a linear system. Now this is all still with the eyes. It will all be simpler, made a lot simpler when we look at a concrete example. So the algebraic derivations are done on this slide. So we have the expressions for the derivative, and then we have the expression for the derivative in the point. So you can again see that the interpretation of the BI is indeed the derivative at the point. So that's the derivative at the right point. So what comes here at this side is actually the same, or it should be the same, as what we have here, but it is expanded. So these two are the same. So what is at the right is the slope condition at the right point, and here I forgot a prime, so there's another bug here. So the slope condition at the right point is the right-hand side, and at the left we have everything the same, but now you can see that the indices, every I is replaced by I minus 1, and the I plus 1 is replaced by I. So these are actually shifted equations. Now we rearrange the terms, so we actually know the divided differences. So these can be computed from the function values and the spacings between the nodes. At the left, we have now a three terms relation. The following example is actually, so we have n equations in n plus 2 unknowns. Notice that the entire problem was a 3n dimensional problem. We have reduced the dimension dramatically. So it's actually now an n-dimensional problem. So what we have accomplished thus far is also a significant reduction in the complexity of this problem. So we have to solve a linear system, but it matters a lot if the dimension is 3n or if it is n. We have two additional unknowns, and we impose the condition that we have a natural spline. All right, and here is the example. So this is an example for n equals 4. So we have a matrix that is actually a 3 by 3 matrix, but it is written in full generality, not yet eliminating the T0 and the T4. So actually the first column here appears with the T0, so if you do the matrix vector multiplication, and the last column, but I'll try to box in here, appears with T4. So we have a 3 by 3 system. And the dimension is just small enough to fit on a slide and just large enough to actually see the structure of the linear system. So the linear system is tri-diagonal. And also you can see that it is diagonally dominant. So this is one of these natural occasions where we have encountered diagonally dominant matrices. The matrices that can be solved efficiently with Jacobi and Gauss-Seidel. So this is very good. So we solve a linear system, but it is a very structured linear system. So this is a quasi-numerical example, so you still have a lot of letters sitting in there. But this slide is complete. So you have the structure of the 3 by 3 linear system. The coefficients can be computed if you have the spacings of the points. And the unknowns are the TIs. When you compute them, you can compute the coefficients. So the BI can already be computed from the divided differences. The CIs and the DIs are computed with the computed TIs, which are proportional to the concavities. All right, the first exercise allows you to verify this. In some sense, you can do everything by hand. You can see the spacings. So the first node is x1, so the first interval is 1, 2. The second interval is 2, 3, and the third interval is 3, 4. So we work on the interval 1, 4. Every h is 1. So the matrix has 2 on the diagonal, 1 off the diagonal. So it's a very simple system, but nevertheless use a computer to solve it. And so that's the first part, solve a linear system, set up the linear system and solve it. So you have to compute the divided differences as well. But dividing by the HIs is very simple. It's each time dividing by 1. So you actually take the differences in the function evaluations. So setting up that linear system can be done by hand. You have to compute it and verify that all the conditions are satisfied. Also here, you can still do this by hand. So there are three, we have 4 points, and there's going to be 12 conditions. We can do everything here still by hand. All right, so we have derived an algorithm to construct these splines. We actually also have proven a theorem. So the system is diagonally dominant. It is a system, again, we shouldn't take nodes that are on top of each other. So we have the same interpolation condition again. We have actually a unique solution. So there is a unique solution that solves the piecewise approximation problem, where we obtain interpolating conditions. Now, the interpolating conditions would not be enough for smoothness, so we will require at all the internal nodes that the points agree. So in a way, this is also more or less guaranteed by the interpolation condition. So these are extra interpolation conditions. And here, I guess I have reformulated it again wrong. So I will fix this. So these indices should be I, not I minus 1. So we have the smoothness of the spline approximation that is given to us by these extra interpolation conditions and the slope and concavity conditions. We have 2 conditions left, and we require that it is a natural spline. So the concavity at the endpoint is 0. No second derivative there. All right. Here is another numerical condition, a numerical exercise. So do this at random, so for random distances. So do a couple of experiments. I mean, one experiment is what the exercise suggests is actually enough. But algorithms typically, when they break, so it becomes poorly conditioned if actually the distances would become closer to 0. Would be. Now we examined the issues that came from the interpolation. That was the van der Monde. Now here we have the diagonally dominant matrices. So if the h's become 0 or get smaller, they still remain diagonally dominant. So that may most likely, so I would encourage you to take smaller values for the HI. Can you actually break the diagonally dominant condition? So that's actually the question for this exercise that underlies it. So generate an example. Perhaps you may want to run this with many values, and sometimes take a value for HI that's, for example, 10 to the power minus 8. What happens if H naught is 10 to the power minus 8? Which would mean that your first interval is very small. What happens if the middle interval is very small? So we have H2, which is at the middle. What if that is 10 to the power minus 8? You study random values, and then you study particular values. So that's actually what the exercise is all about. All right, splines, an application in computer-aided design in manufacturing. So this picture is made with Tixi, which is a LaTeX package, and the Tixi commands actually follow also the Bézier curves. So what is a Bézier curve? It's also a piecewise approximation, but now instead of having the data points, so you do have data points, but the data points are actually the arrows. So there are controls. So here you see what we have. We have two knots. We have knot 1, 1 and knot 2, 2. So in some sense, we go from 1, 1 to 2, 2. But we could do this in a straight line, but that's rather boring. So what the Bézier curves allows you to do is that you say that the slope, if you depart from the knot 1, 1, the slope should go upward. So actually you go to the point 1, 3. And when you come in to the second knot, actually you come in at the direction 3, 3. So it's like if you would leave from the knot 2, 2, if you would return from 2, 2 to 1, 1, you would actually not go, you would go first in the opposite direction. So that is what these arrows indicate. So arrows, they have direction and they have a magnitude. So with the direction, you can indicate the slope, the direction of the slope. With the magnitude of the arrows, you can control how much the slope should go, how much you should go in a particular direction. So we will derive the formulas to draw this, to define this curve. So there is one curve, but there are two functions. So very important that you actually realize the difference between a function and a curve. A curve is defined by two functions, x and y, in function of a parameter. So this is also a one-dimensional plot. But this is not a function. So y is not a function of x. So you see that at there are two values for y. So this is not a function. So you cannot plot this as a function. So in a way, in an MCS 320 course, it's important if you draw a plane in the plane that you make the distinction between what is a curve and what is a function. All right, let us define the Bézier curve. So the Bézier curve is actually defined by 4 points, and they are listed in this order here. So on the previous slide, I said we were going from one knot to the other. Here we have where the curve begins is the first point, and where the curve ends, last point. So these are the interpolation conditions on the piece of the Bézier curve. So a Bézier curve will consist of many, many pieces. If we can do one piece, we can do the whole curve. Then the points 2 and 3 here are the controls. So they are the coordinates. So on the example on the previous slide, we went from 1, 1 with the control actually to 1, 3. And then from the endpoint, the endpoint was 2, we went to 3, 3. So I remember what is on the previous slide. So it's good if you now have the slides handy to see the slides next to each other. So on the previous slide we had the numbers. Here we have the variables that we are going to use. Now I was talking on the previous slide about the difference between functions and curves. Now we have two cubic functions, x of t and y of t. And these two functions are defined in t, where t ranges from 0 to 1. A very natural choice. And you can already see that we know one of the coefficients of the two functions. So the constant coefficients is where we begin our curve. So we have 8 coefficients on input, 8 coefficients on output. So it's then an indication, a very strong indication actually, that this problem will have a unique solution. Now again, we could solve this with a linear system. So if you would not go through what we're going through in the next slides, if you do not want to go through that, well, you can set up the conditions for the linear system. So this would give us again a van der Monde system. So we actually would set up the linear equations or a van der Monde type. Except that now actually we have also conditions on the derivative. So we're going to define the conditions on the coefficients. So we have slope conditions. So at the beginning, we have our first control. So we take the derivative, and that means that the first derivative will give us a condition on the bx, on the second coefficient. You see, we don't really need to solve a linear system to know the other coefficients. So bx can be computed just by a simple difference. And the cubic, you see a lot of 3's there, and that's because actually we work with cubics. So we have the other interpolation condition that we're going to work in now. So we have one control condition. We have the interpolation condition, and that then gives rise to a condition that involves the dx and the cx. So imposing the condition that at x1 we have x4 gives us an equation in dx, and we can solve for cx using what we obtained for the equation that I just underlined here. And then we also have this additional condition here. So this actually allows us to eliminate the dx, and that is done here. So this equation, what I just underlined, the last one that I underlined, is actually writing dx as x4 minus x1 minus bx minus cx. So one can see now that we have eliminated dx from this. So here, actually, I wrote it here as well. So the bx is eliminated as well. And then we have one expression in the coordinates, the x coordinates, that allows us to derive the expression for Cx. So you can, if you compute, if you want to be frugal with your computations, so you compute Bx first, and then you compute Cx as using the value for Bx. So by the way, I'm doing everything now for the first x function. For y, it will be the same. Let me conclude, indicate that we have all the coefficients. We have bx, so that is this one. We have cx, and then we have dx. So 1, 2, and 3. So that's actually the algorithm. 3 steps for 3 coefficients. The first coefficient we got from just copying the x-coordinate of the first point. Everything is the same if you do this for y. So you replace all the letters x by y, and you go through the same process. All right, so let us verify that everything is fine here. So we compute all the formulas are actually given here. So in a way, the purpose of this slide is actually the transition from the mathematical algorithm to the Julia function. So there will be one Julia function that computes the 8 coefficients for the 2 cubic splines that define the Bézier, the piece of the Bézier curve. So what we have is that we have the derivatives at the one endpoint, and then we also verify the slope condition at the other endpoint. So why do we do this? We have the controls. So here actually you see that the controls are satisfied for the endpoints. All right, then. Here is the example again. So this was our beginning example. We have 2 knots and 2 controls. So here I wrote it again with 2 knots, and then their controls. But we will write 1, 1, then 1, 3, then 3, 3, and 2, 2. So the difficulty that only remains is that you have to remember that in the notation, the controls and the knots of the second point are swapped. All right, so we will compute these coefficients here. So this is a very nice example that can still be done, everything can still be done by hand. In the time of paper by pencil. Although drawing the curve, I would actually not recommend that you do this by hand. All right, then all algorithms in this course are defined by Julia functions. So then here is the Julia function that defines one piece of the Bézier curve. So we have 2 arrays on input. So they are not lists of tuples. That could have been another input. We return the coefficients of the cubic splines. You see that the x1 and the y1 are immediately copied. And we have the formulas, so the 3 steps. So we compute the B, the C, and the D. So there are 3 steps, and everything is symmetrical for the X and the Y. All right. The command line execution, or actually the code, what is on the previous slide is copied into the Jupyter notebook that is posted. What is important is that, and I should probably have written everything out here. Let me do this now. So I had the first 0.11 with its control, which was 1, 3. And then I have the second control, which is 3, 3. So that's written at the third position. And then I had my last knot, which is 2, 2. So these are the 4 tuples that are given on input. The x's are now actually here stored in the A array. So 1, 1, 3, 2 for the x coordinates, the values for the x coordinates, and the values for the y coordinates are also listed as 1, 3, 3, 2. And then we see the coefficients for the 2 cubic splines coming up. They're all exact integers. All right, so let's check this. So if we have a curve, so there is the very useful eval poly command. So we evaluate the coefficients for x and y at 0 and 1, and we then indeed find that the curve that we constructed interpolates. We could continue our verification with the derivatives and verify that the slope conditions match. But it's probably better to look at the plot. So here is the plot. So now all the plots 4 were made with Tixi. This is a plot that is made by Julia, where we start from 1, 1. And we go to 2 in a very special way. So this is a curve, not a function. And you can see that this is a very flexible mechanism. If you want the curvature, the slope to go a little bit, if you want to diminish this curve here, you would diminish this arrow. So we had the arrow that is going here for the control, make this arrow smaller, and you will, or larger if you like, and the shape will change. So this is extremely flexible. If we are curious for the plotting instruction, so 2 functions are defined. So the plotting is now the plotting of a curve, and in order to plot curves, you have to sample the points. We define the functions, and after defining the function, we define a range. The range from 0 to 1 with a step of 100. That makes it really look very smooth. And then the plot is being made, turning off the legend. And I want the same spacing for, so the aspect ratio is actually here now important. Otherwise, the window gets adjusted automatically and you don't see the correct slopes. All right, so let's do this yourself. Here now we have 2 pieces of a Bézier curve. So let's design this. So run the Bézier function twice, once on the first set of 4 points and once on the second set of 4 points, and then do the plot also twice. So this is just to verify that you can compute with these Bézier curves. All right, then we close off another chapter. I can summarize what we have covered in these 4 last lectures, and not anymore in 4 sentences, although I can try. So in the first lecture, we can compute a unique solution, and that unique solution could be the solution to the coefficient problem. or to the value problem, and that is respectively be done by the method of Lagrange or Neville. The second lecture on interpolation had its focus on Newton interpolation. So it's an iterative method as well. We actually then derived also the next term rule, when to stop using more and more interpolation points. So Newton is very good because it solves both the coefficient and the value problem. And we actually applied Newton then again in the lecture where we had our focus on choosing our interpolation points so that we have a better interpolation problem. So we ended that lecture with rational approximations. So in a way, in this chapter, we have seen three types of interpolation. You can, an approximation, either you are computing one large degree polynomial. You can also compute a quotient of two polynomials. So this is the rational approximation, starting actually from Taylor series coefficients. So the Taylor series, if you can take derivatives, is actually our first approximation. But the problem with the Taylor series is that they're only valid in a very small range, close to zero. All right, and today we did the cubic interpolating splines that are very smooth, and they have the advantage to work with very low degree polynomials. So they are very efficient to construct. And something that I should have pointed out is that it's also a data transformation. So what you have is you have 8 points for one piece. So you have 2 knots and 2 controls, 8 coefficients, and you're going to replace that data by 2 cubic splines, also defined by 8 points. So in terms of data, and it's now actually, perhaps I should have emphasized this right from the start, this is a linear transformation. So cubic interpolating splines will scale extremely well because they have this local aspect. So we've seen that the cost of interpolation is quadratic in the number of points. Here actually we have a linear cost. So this is probably something that I should point out, and that here where I end with is that the cost of this is linear in the number of points.